In the previous lecture, we classified the states in a Markov chain as transient and recurrent. Now we will continue with some further classifications. First of all, for a recurrent state, for I recurrent, I is called null recurrent if the expected time to return to this state, given that we started in this state, is infinite. In other words, the mean recurrence time is infinite. This cannot occur in a finite state space, in other words, a finite state Markov chain, but it is possible in a countable state Markov chain. Now, an immediate theorem that will follow from this definition is that a recurrent state is null recurrent if and only if pii of n goes to 0 as n goes to infinity. Right. This is quite easy to prove, and I leave it as exercise to you. Now, we will now make another definition. The period d of I of a state I is defined as the greatest common divisor of values of n such that pii of n is different from 0. That is, this is the greatest common divisor of epochs at which return to state I is possible. So I is periodic if d of I is bigger than 1, and it's said to be aperiodic if the period is 1. Let's give some examples. Take this three-state Markov chain, where each transition out of state 1 goes to state 2. Each transition out of state 2 goes to state 3. And each transition from 3 go to 1. Clearly, if you look at values of n for which p11 of n is different from 0, suppose we started at state 1, okay, we can come back to state 1 in 3 or 6 or 9 or 12 and so on number of steps. So pii of n is greater than 0 only if n is a multiple of k, 3. Right, so here the period of state 1 is 3. The period of any state in this Markov chain is 3. It is clear to see in this example, but it is possible to prove that if we have a recurrent class of states, we will define what the recurrent class is later. Each state has the same period. It's something that we may prove later on, or you could try to prove as exercise. Let's see another example. Let's call this example 1. Example 2 could be a little bit more non-trivial, perhaps. We have 1, 2, and 3, and they form a cycle just like this one, except now we're adding states 4 and 5, such that from 3 you can go to 4, from 4 to 5, and from 5 back to 3. Now let's again focus on state 1, and suppose we started in state 1. What are values of n such that p11 of n is non-zero? Well, we cannot come back to 1 in fewer than 3 steps. So the smallest value of n is 3. 6 is possible. 6 is possible by doing this circle, or going from 3 to 4 to 5 to 3. Oh, let's see. We can go from 1 to 2 to 3, that is 2 transitions, and then 4, 5 back to 3, that is 5 transitions, and go to 1. So 3, 6, 9, etc. So apparently here the smallest n, the greatest common divisor of values of n for which p1 of n is non-zero is 3. Okay, so let's say GCD of these things is 3. Let's focus on state 5. 5 to 3 to 4 to 5, 3, and similarly 6, etc. So what if we added one more state here, for example, state 6, and modified the Markov chain like this? I'm going to use another color to denote this modification. Now, this cycle has length 4. So in the modified Markov chain, we have, let's see, possible ways of going from 1 back to 1. So we can go from 1 back to 1 in 3 steps. Or 3 plus 4, 7, say 1, 2, 3, 4, 5, 6, 7, and so on. Automatically, it is easy to see that the greatest common divisor is going to be 1. So adding this cycle destroyed the periodicity in the Markov chain. There could be another way of destroying the periodicity. Let's see another example. 1, 2, 3. Very simple cycle, except I'm going to add a self-transition. My claim is, if you add a self-transition to a recurrent class, you destroy periodicity. And it's very easy to prove, because if you add a self-transition, if Pii of n is non-zero for a given n, it is non-zero for n plus 1. And clearly, by this reasoning, the greatest common divisor is going to be 1. So this is aperiodic because of the self-transition. Now, let's return to our definition of null recurrence, because I'm going to be now making a definition of another important classification of a state. The definition is the following. A state is called ergodic, okay, if it is recurrent, non-null, and aperiodic. Okay, a state is ergodic if it is recurrent but non-null, so that it will keep getting revisited with probability 1, and aperiodic. Now, why does periodicity ruin ergodicity? We will see in upcoming examples in other lectures. But for the moment, I just want to give you an example. Of course, in order to talk about null recurrence, we need to be in a Markov chain which has a countably infinite number of states. So that's the example that I'm going to give you. Let's consider a simple random walk. The simple random walk is constructed as the following. From any state with probability p, you go to the next state down the road, or you go backwards. Okay, the probability that you go to the right is p, probability you go to the left is 1 minus p. Similarly, from 1 you go to 2 with probability p. You go from 2 back to 1 with probability 1 minus p. You go from 1 to 0 with probability 1 minus p, and so on and so forth. And this has a countably infinite number of states. Clearly, this Markov chain is periodic with period 2. Okay, so states in this Markov chain are not going to be ergodic. Are the states transient or recurrent? There are two possibilities. The states are all transient if p is not equal to 1/2. Because if p is not equal to 1/2, the state is either drifting to the right. If p is larger than 1/2, it's drifting to the right. Or maybe to you this is left. And if the p is less than 1/2, the state is drifting to more negative, to negative infinity, essentially, this way. Only when p is equal to 1/2, all the states are null recurrent, meaning they are recurrent. They will get revisited with probability 1, but the expected time until we return to each state, given that we leave it, is infinite. So they are null recurrent if p is equal to 1/2. Building on these classification concepts, in the next lecture, we will try to classify Markov chains.